When a nation successfully launches an Earth observation satellite, the public naturally assumes the hardware remains in orbit, forming a permanent, watchful constellation. After Kenya launched the highly publicized Taifa 1 in 2023, that exact assumption took root across the country. Yet, the scientific reality is quite different. As of April 2026, Kenya currently possesses 0 independent satellites in low Earth orbit. The nation's historic precursors, 1KUNSPF, Simba, and Taifa 1, have all yielded to the immutable laws of orbital mechanics. They decayed over time and safely burned up in the Earth's upper atmosphere. While these empty orbits might suggest a setback, they marked a transition toward a more resilient architecture, one that doesn't rely on the survival of a single unshielded satellite. On April 11, 2026, the Kenya Space Agency, operating as part of a tri-national consortium alongside Egypt and Uganda, launched the ClimCam mission. Instead of deploying another exposed standalone satellite, this consortium opted to host an artificial intelligence-powered payload directly on the exterior of the European Columbus module on the International Space Station. This tri-national collaboration prioritizes the utility of the climate data over the prestige of owning independent hardware. It's a model designed to ensure that critical data flows continuously, even when space weather is at its most volatile. The loss of Taifa 1 provides a perfect case study in these orbital vulnerabilities. This was a state-of-the-art 50 million shilling observation satellite, projected to last 5 years, yet it burned up in 2025, barely halfway through its intended mission. The primary culprit for this accelerated decay was the unexpectedly fierce maximum phase of solar cycle 25. During a solar maximum, the sun's magnetic poles complexify, unleashing immense quantities of extreme ultraviolet radiation and highly charged particles across the solar system. When intense solar radiation hits Earth, it's absorbed by the thermosphere. This energy causes the gases to heat and physically expand outward into higher altitudes. For a small satellite in low Earth orbit, this expanded density acts like a sudden invisible wall of fluid. Plowing through these denser gas particles at 28,000 kilometers per hour generates severe aerodynamic friction, a destructive force known as atmospheric drag. The global aerospace industry relies on forecasting tools like the Shatton model to predict this drag, but these standard models systematically underpredicted the sheer ferocity of this specific solar cycle. Large, heavily funded telecommunications satellites survive this friction by routinely firing onboard propulsion systems, physically raising their altitude when their orbits inevitably degrade. Small CubeSats, however, operate under highly constrained mass and volume limits. They lack the mechanical space for meaningful onboard propulsion capabilities. Without the ability to manually boost their own orbit, unpropelled nanosatellites are mathematically guaranteed to succumb to the swelling atmosphere during a solar maximum. To maintain continuous observation, Kenya needed a totally new infrastructure approach. Faced with the extreme financial and operational risks of launching replacement nanosatellites, the Kenya Space Agency pivoted to a model of shared orbital infrastructure. Through the UN Access to Space for All initiative, the tri-national consortium secured a spot to host their 3.5-kilogram payload on the Airbus Bartolomeo platform. This instrument sits securely attached to the exterior of the International Space Station, orbiting at an altitude of roughly 400 kilometers. A standard 3-unit CubeSat weighs a few kilograms and is entirely at the mercy of atmospheric drag. The International Space Station, by contrast, is a massive 420-ton structure. Because of its size and strategic importance, the ISS utilizes regular cargo resupply missions and dedicated maneuvering thrusters to perform routine reboost maneuvers, constantly raising its orbit against the drag. The Bartolomeo platform also provides hosted payloads with an uninterrupted, stable power supply, completely overcoming the electrical constraints that usually limit small, independent satellites. By physically attaching to the space station, the consortium effectively outsourced its propulsion and orbital maintenance. This single engineering decision entirely neutralized the physical threats of atmospheric drag, securing a permanent observation deck over East Africa. While hosting on the ISS solves the physics problem, it introduces a severe computational constraint. The ClimCam payload is allocated a highly restricted downlink length of just 0.1 megabits per second. Traditional observation satellites act as orbital dumb cameras, capturing massive volumes of raw data. As this diagram shows, transmitting uncompressed image files over restricted links creates a severe bandwidth bottleneck. ClimCam solves this by deploying an advanced convolutional neural network onto an onboard edge AI chip. The system is equipped with a high-resolution RGB optical camera, capturing the visible and near-infrared spectrum across 3 distinct bands, from 0.4 to 0.7 micrometers. As the ISS flies over East Africa at 28,000 kilometers per hour, the onboard AI analyzes this multispectral imagery in real time. The neural network is meticulously trained to identify specific biological markers, like early chlorophyll degradation, that indicate severe water stress or initial fungal infection in crops. The algorithm detects asymptomatic physiological changes with over 90% accuracy, recognizing crop failure long before any wilting or discoloration is visible to a farmer on the ground. Because of this edge processing, the payload can discard the heavy raw image files entirely. It only beams down the lightweight binary warning alerts and precise geographic coordinates. Processing these complex inferences in orbit allows the mission to overcome the physical limits of its data link. It converts a narrow connection into a stream of high-velocity intelligence. This map charts Kenya's 2026 extreme weather zones. The country battles climate whiplash, an aggressive oscillation between severe droughts and catastrophic rainfall. While exceptional storms dump rain over Nairobi and the Lake Victoria Basin, coastal counties endure extreme heat and prolonged drought. These extremes carry devastating consequences, compounding the damage from 5 consecutive failed rainy seasons that decimated livestock herds across the vast arid and semi-arid lands. Traditional ground-based weather monitoring stations are spaced too far apart to accurately predict the rapid microclimate shifts occurring across these diverse landscapes. The unique orbital trajectory of the ISS allows the ClimCam payload to pass directly over the East African region up to 4 times per day, providing the continuous, high-frequency surveillance required to track these shifting conditions. To process this continuous feed, the Kenyan government overhauled its data governance architecture. The newly formed National Earth Observation Data Council dismantles historical bureaucratic silos, ensuring intelligence is shared instantly across all ministries. The physical alerts are received seamlessly through the Sayari ground station in Nairobi, which was recently modernized in partnership with the French infrastructure firm Skynopi. The final and most critical step of this pipeline is translating complex space telemetry into a format accessible to smallholder farmers, utilizing basic mobile technology. If the orbital AI detects critically low soil moisture in a specific agricultural ward, it instantly triggers an automated SMS alert costing just 1 shilling. The message advises the local farmer to abandon water-intensive maize and immediately switch to resilient, short-cycle beans. The ClimCam architecture demonstrates that space sovereignty relies on engineering a system that bypasses foreign data dependency, delivering real-time, life-saving intelligence directly to the soil.